Watch a robotic assembly line moving at maximum speed, or a sorting terminal operating flawlessly, and it is easy to assume the network is healthy. But assuming local efficiency equals systemic success is a trap. Cutting costs in a single warehouse or pushing a machine to its absolute limit often creates bottlenecks downstream or spikes inventory holding costs. Isolated improvements are not the same as optimization. To fix a disconnected network, we have to look at the formal, mathematical discipline of supply chain optimization. In supply chain logic, planning is deciding what should happen. Execution is making that plan happen physically. Optimization operates on an entirely different layer. It's the deliberate calculation of what is best for the entire system, consciously ignoring local metrics to serve the whole. To find the best possible overall outcome, you often have to intentionally slow down one node or spend more capital in one department to protect the end-to-end flow. If an action boosts a single departmental KPI but degrades total network performance, it completely violates the mathematical purpose of optimization. The Apex and Oliver White standard definition specifies that optimization actions redesign flows so the entire supply chain performs better. Notice the requirements. Decisions must be system-level, require explicit priorities, and demand conscious trade-offs. This explicitly rules out KPI gaming or applying lean everywhere. Trying to make every single department faster and cheaper simultaneously is a mathematical impossibility in a constrained system. Pushing a single manufacturing plant to maximum utilization without aligning to downstream demand inevitably generates excess inventory and ties up critical working capital. The absolute rule is right here. If an action improves one area but hurts the total system, it is not optimization. The success of the network is measured strictly by the final outcome, rendering the maximization of any isolated metric irrelevant. To shift a system's operating point, we manipulate three structural levers. First, the objective function dictates what the system solves for, like cost to serve or cash to cash. Without it, optimization is impossible. Second, constraints define the strict physical and financial limits of your network. True optimization calculates the best path forward given the exact capacity and capital you actually have, rather than pretending those limits do not exist. Finally, we have decision variables. These are the physical nodes and policy rules that management actually has the authority to change. You can reposition safety stock across different echelons, adjust your planning time fences, or completely redesign your distribution network footprint. Optimization requires deliberately manipulating those decision variables, strictly bounded by your constraints, to maximize your single objective function. This table shows why continuous improvement differs from optimization. Improvement chases a single KPI, while optimization relies on calculated trade-offs. This requires building a strategy-driven architecture, shifting from making local operations faster to accepting local friction for a better total outcome. A company can run continuous improvement projects for years, steadily increasing isolated metrics, and still completely fail to optimize its supply chain. Moving inventory or capital around the board is allocation, but allocation by itself is not optimization. Looking at this matrix, we see three interdependent elements that must exist together: resource allocation, the objective function, and constraints. Here's what happens when you allocate without the other variables. If you push more inventory to all distribution centers, local service improves, but ignoring financial constraints means the total cash requirement explodes, tying up capital needed elsewhere. Take away any single piece of that triad, and your strategic move degrades into a blind adjustment. A decision achieves true optimization status exclusively when allocation, objectives, and constraints are aligned simultaneously. Optimization operates within closed bounds. As this definition states, reallocation means shifting existing resources. No new resources are added to the system. You cannot instantly summon warehouse capacity, extra labor hours, or working capital. This comparison highlights the difference. An adjustment changes one local parameter. True reallocation shifts mass across the end-to-end network, demanding a conscious trade-off. You deliberately sacrifice performance in one node to win in another. If management proposes a new process but cannot answer what metric they are giving up, it is likely not a true reallocation. Optimization is not equivalent to growth or capital investment. It is the strict redistribution of existing mass to generate greater total value. Let's apply these theoretical boundaries to standard physical operations. Looking at this inventory example, a standard lean approach tells you to reduce stock everywhere. Optimization tells you to reallocate inventory to decouple variability. By placing buffers strategically rather than cutting them universally, you maintain the same final service level while lowering total systemic stock. In transportation, the objective is balancing shipment frequency against inventory holding costs to lower the total landed cost. If a logistics manager simply tries to minimize freight cost per shipment by holding full truckloads, they will inflate inventory levels and damage the cash cycle. Practical operations require identifying exactly where you must accept a localized sacrifice to secure a mathematically superior global outcome. Optimization is a strategic management discipline. Equating it to simple cost-cutting or localized efficiency creates systemic failure. This document establishes the absolute baseline. A supply chain is optimized only when the weakest constraint and the highest value objective are aligned. To evaluate any proposed supply chain action, you have to run it through a strict diagnostic test. You must answer 3 specific questions: compared to what alternative, for which objective, and under which constraint. If your team cannot answer those questions explicitly, the action they are taking is merely an allocation of resources. An optimized supply chain is ultimately the highest value mathematical alignment between a system's constraints and its primary objective function.